Okay, good. So, guys, our event is slowly coming to the end, and that's why we have the sweetest talk in the end. So, basically, this is Almudena Carrera, and today I already, you remember, showing to you this slide, yeah, that's why not to connect to quantum computers classically and to get like a little bit more qubits. And it occurs that if you do this, then you're going to have a Nature publication. So basically, we have the person in the audience who has a Nature publication. And I mean, not Nature Communications, not Nature Methods, whatever, it's nature.com. So like the best one. This is Almudena. So this is all what I read about her on the internet. All the rest, she can speak for herself. So please, the stage is yours.
So I'm a researcher in algorithms at IBM, and today I will give you just an overview of the activities that we have and a bit from the algorithm and from the hardware perspective. But as a disclaimer, I do research on the theoretical part and the theoretical activities. Yes. So yes, my topics of research are on algorithms, but a bit more fundamental. So if you have any questions, please feel free to stop me, but just bear in mind if it's about the hardware, about cables and stuff, probably I cannot answer those things. So a bit of a motivation of what's the motive for IBM to do quantum computing. There is two main goals. One is to bring useful quantum computing, and that means coming up with algorithms that have practical applications, not just doing something on a quantum computer because you can, but something that has actually practical impact. And then secondly, once you have good quantum computers, we have this famous algorithm by SOR to factor numbers that will break cryptography. So the goal is also to bring classical methods to encrypt classical data that cannot be broken by a quantum computer. And today I will be focusing on the first one because that's where we work in the algorithms part. So how do we do the first one? It's also a bit of a twofold. We have to develop the hardware and create a scalable platform that scales better than classical. And then on the other hand, for the algorithms, now we are creating a network of people, academics and industry, to work on the different topics of research, because now we are at the point where we have to identify points in the classical community where classically it's very hard and it is also useful. And we as quantum researchers, maybe we know about quantum, but we don't know about maybe, I know, chemistry or whatever. So we are coming up with people also from the classical community to identify what are these problems that are very hard classically and are probably classically hard, and that there is some hope that we can solve with a quantum computer. So I don't know if you heard that there is now some working groups, and the topics of these working groups are high energy physics, optimization, materials, healthcare and science, and sustainability. And basically the goal is to gather people from the community that are experts in the field and try to come up with quantum algorithms for these problems. Now, as I said, there is a bunch of NP hard problems, and then there is a bunch of problems that are classically quantumly easy. And now what we want to identify is those that fall within where these two sets meet, but that they are not classically easily, because if you can do it with a classical computer, it just doesn't make any sense to do it on a quantum computer. So a bit of an overview of the path. In this graph here, you can see the years and then the estimated average number of qubits that people were using in our hardware. And you can see that the trend was slowly increasing over the years. But had we kept it this way, we wouldn't have reached the 100 barrier until 2040. And now what happened is that you need some breakthroughs in order to make this curve go a bit more exponentially. And 2 years ago, it's when we started to run things already more than 100 qubits. And you can see here that in 2023, it was an average of 13 qubits, which is not a lot. Suddenly in 2024, it was 40 qubits, and now we are at more than 100 qubits on average, which is quite impressive. So I started in 2018 at IBM, and I remember that if we could run on 5 qubits, that was already an achievement. So why is this trend so slow? We have been having chips with, say, 50 qubits for a long time, so why were we not using it? And the reason is because the qubits are noisy and the operations are noisy. And now to deal with errors, there are two approaches. One is error mitigation, and the other one is error correction. So what's the difference? So error mitigation, you perform the computation on the physical qubits themselves. And then what you do is you take out the results of many noisy runs and you combine them somehow classically, and then you obtain a final result that has less noise. On the other hand, error correction, then you compute on qubits that are already what it's called logical qubits. So one logical qubit is encoded on a bunch of physical qubits, so more than one. And I will explain later a bit like the rough idea of how this works. So how do they compare? Error correction is performed only on Clifford plus T gates, because we only know how to do error correction on these types of gates. And error mitigation, you can do it on any gate. So for example, CNOTs or any rotations. Now, qubit overhead, error mitigation has none. You just run your circuits. And error correction has a large overhead because for each logical qubits that you use, you need to use many physical qubits. Now, circuit output, an error-corrected circuit, you can get any type of output, while error mitigation, you can only apply it for expectation values. Then as for the sampling overhead, error correction has none, but error mitigation here is where you have to pay the price. I mentioned that you need to combine many noisy outcomes, and this is where the overhead comes, and this is large. Now, how large are these two large? In the case of error mitigation, it's exponential in the number of qubits, and in the case of error correction, it stays polynomial. So in the long term, it's error correction is the goal, but at the moment, we can only afford error mitigation. And here is a bit of a hand-wavy graph, but I like it because it gives a good intuition of how these methods compare. So imagine that you have a problem for which you have a good quantum algorithm that performs, say, exponentially better than classical. And here you have the size of your problem, and here the runtime. So classically, you would expect that for a very hard problem, it just grows exponentially the runtime. Now, error mitigation, you have a very good quantum algorithm, but as the number of qubits increases, the noise increases, and the price that you need to pay for error mitigation becomes exponential. So it's also a kind of exponential curve, but the lower the physical noise that you have, the flatter this thing becomes. And finally, you have quantum error correction that has a very large overhead, but then your runtime stays good. The one stays true to the runtime of the good algorithm that you had. So I don't know if you heard that 2 years ago, there was a big noisy paper that IBM reached quantum utility. It was the first time that we ran on more than 100 qubits. And this is what we call quantum utility. So what is quantum utility and how does it differ from quantum advantage? So quantum utility, we defined it as a demonstration that a quantum computer can run a quantum circuit beyond the ability of what classical computers can simulate. And then quantum advantage is a demonstration in which you can run a quantum circuit, but you can solve a problem that it's either more efficient or more accurate or more cheaper than on a classical computer. Yeah, that's the main difference. Now, what we expect, I will go a bit more into this utility, but what we expect is that in the near future, there will be claims to advantage, and it will be a bit of a back and forth between the classical community and the quantum community. So we come up with an algorithm and say, like here, we run it, we achieved quantum advantage. And then from the classical community, they will come up with better algorithms to push the boundaries. So we expect that it will not be like we achieve quantum advantage, that's it. We expect that it's a bit of a back and forth, and at some point, it will be quantum advantage. So before error mitigation at a big scale and utility, all the circuits that we were running, you could simulate them on your laptop pretty easily. So this utility era is it's the era in which we cannot just simulate the circuits, but we need to come up with clever classical methods to check whether the solution actually from the quantum computer actually is valid. And then later on, in 2029 is when IBM has said that there will be fault tolerance devices. That's the idea. So I want to show a plot from this paper because this was the first time that you could just not simulate the the quantum algorithm with a classical computer. And in fact, when the paper came out, very shortly there were many papers on how to simulate this circuit classically. And then if you put all the results on a line of the different methods, you realize that they do not agree with each other. So we are at the point, the quantum results are these blue crosses, and all the other points are from classical methods. And you can see that they all fall within the same region, but they do not agree with each other. So we are at the point, so we as researchers, we are at the point where we have to talk with classical people and come up with methods to simulate and somehow validate what we are running, because there is now no way to check anymore that the result it was right. When I started, I could just run classically a simulation of the quantum circuit and say, yes, it matches more or less the hardware. And now we really need to think of how to do this classically. So this was the first breakthrough that there was in 2023, and there was a second one last year, and this is on error correction. I will explain a bit more in detail what this means and why there was a problem in this area. But basically, what you should take as a take-home message is that there's been two big breakthroughs from IBM. One was the utility paper, and the other one was on error correction. So I want to show the roadmap just to give an idea of where we are at and what are we looking into the future. And for now, let's just focus on the bottom row, which is, maybe I can. Okay. Yeah, the bottom row is the different devices that we had. So from here up to here, this is what it's been deployed. That was up to last year. And the number here is the number of qubits. And you can see that from here up to here, the number of qubits has been increasing. Here it was up to 27, and suddenly there was the big jump with 127 qubits, which is the device that they used to run this utility experiment for which I showed you the graph before. Now, for this year, they plan to deploy a different kind of chip. This one has less qubits than the one before. This is 133, this is 120. But there is something else going on that I want to explain a bit later. But one thing to notice is that now in the coming chips up to here, what you can see is that they are not just a single chip, but they start being connected. This is based on something what Pavel mentioned earlier, a paper that we published on how to run a circuit that spans two different chips via classical communication. And this is the idea. I think this one will be quantum communication cables. And yeah, the idea is that the quantum chips will be modular. So for the very first part, up to the heron, not only the number of qubits was increasing, but also the accuracy of the gate. And now we are in the order of 10 to the minus 3. Now, this 10 to the minus 3 is important because it's when error correction starts to be feasible. So to do error correction, you need a good enough hardware, so good enough noisy operations. And this is starting to be the regime where you can start speaking about that. Now, I mentioned that at some point the chips went from just increasing the qubits to something else. So the older chips, they had this type of coupling map or connectivity graph, and all the qubits had between 2 and 3 connections. In the new one, they will have 4 connections. So why is this important? Whenever you have a circuit and want to map it to something like that, in most applications you require, if not all to all connectivity, pretty close to that. And then you need to come up with ways to how to connect in an efficient way, for example, this qubit to this one. You can either do that with a lot of swap gates, which involve a lot of CNOTs and therefore a lot of noise, or you can do circuit cutting, which is a technique where instead of implementing this gate, you simulate it as many circuits, but with only local operations. The problem is you can do that for a constant number of gates that you want to, say, cut. You cannot do that arbitrarily for many because the price for that is similar to error mitigation. It becomes exponential. So having more connections should be a lot better if you want to run circuits on the physical qubits. Now, for the second part that I left out and that it's being hidden behind this, from here on, it's when there will be error-corrected chips. So this one will be the first one. It's called Starling, and it will have 200 logical qubits. The one that's hidden behind here, it's called Blue Jay with 2000 logical qubits. So what does this mean? To put it a bit into perspective, if we are speaking about logical qubits, meaning no error, and the reason I'm saying that is because if your qubits are noisy, you can simulate it classically more efficiently. Basically, the more noise, the easier it is to simulate it. So if we just have logical qubits, 30 qubits, it's what you could do with a powerful laptop, so probably something better than this. 48 with a supercomputing is what you can simulate. Already at 60 qubits, you cannot do it with all of the computers combined. And 200, which is Starling, the first fault tolerance, that's where you are at. So I mentioned that there was a second breakthrough, and I don't want to go too technical, but in order to understand why or what problems they were trying to solve, it is to get I find it useful to get a picture of what is error correction. So one very naive way to implement error correction is you say, okay, I take my qubit, and instead of representing it with one qubit, I will represent it with 3. So a 0 will be 0, 0, 0, and a 1 will be 1, 1, 1. And then what you can do is that you can detect bit flips, because now if, say, there is a bit flip on one qubit, if you do majority voting, then you can say, there was one error because 2 qubits are the same, one is different, therefore the correct value should be the one of the 2 qubits. Now the problem is that, okay, now you have 3 qubits, but how do you detect the errors? Because you cannot measure this without destroying it. So what you do is you add 2 more qubits, and this is done to detect the parity. So in this qubit, you encode the parity of these 2 qubits, and in this qubit here, you encode the parity of these 2 qubits, the parity meaning whether they are equal or not. And then you measure these 2 guys here, and you can measure this without destroying the information here. So you've come up with a way to detect errors. So if we see a 1 here, but a 0 here, it means that the problem was this qubit here, the bit flip was here, and therefore you can apply a correcting gate in here. If you see a 0 here and a 1 here, you can map it to which qubit was the erroneous one. And more generally, you can build the lookup table that maps the outcomes of the measurements, which are called the syndromes, to operations that you can apply on your qubits to correct bit flips. So here I show you how to correct a single bit flip by encoding 1 qubit on 3 qubits. Now, 1 bit flip is not very useful because likely there will be more than 1 bit flip in your circuit. So the next step would be to say, okay, so 1 qubit I encode it in 5, and now I can correct 2 bit flips. And more generally, if you increase the number of physical qubits that you use to encode a single logical qubit, you can correct more errors. Now, the way that you map the errors to these syndromes, this was one way, but you can do more complicated ways, more clever ways to try to encode in the least amount of information all the errors that occur. And then the next step would be to mapping these syndromes to operations that you apply to correct, and this is called the decoding operation. Different ways to do this, they're called the different correction code, and they all have different pros and cons. So up to now, it was, yes?
It's game they also there's on the physical hardware.
There.
If there's an error there, then you cannot rely on that the results in your code.
So in the example, suppose that you have 5 qubits. Okay, the idea is that you do also a lot of measurements. And if you have a lot more qubits, there is some redundancy in the system. This is like a very naive example to only correct a bit flip happening on one of those 3. But yes, the idea is that you need to have a lot of redundancy, a lot of measurements, because the measurements can be noisy, and a lot of operations in general just to correct a bunch of errors. I'm not an expert in the topic, but kind of the intuition is that you need to have a lot of physical qubits and a lot of operations kind of to encode redundancy and be able to correct for errors that happen. Now, this is something that you have to do also in real time, because this I just show you how to store a single qubit. Like, we are not even doing anything with it. We are just keeping it in the 0 or 1 state. So this is why we say that fault tolerance computing has a lot of overhead, because you just have to imagine that this scales a lot more because we have a more complicated code that it's doing a lot more things in the background. And this was just to keep the memory alive. But then if you want to implement a CNOT gate, for example, you will have to do more things. So that's why it's a big research question how to do this in practice. And up to the paper that I showed you earlier, it was believed that only one type of codes were useful for quantum computing, and that was the surface codes, which is what Google has. Now, in the surface codes, roughly to encode a logical qubit, you need 2,000 physical qubits, which is quite a lot. And in this paper, they show how to use different types of codes, which are called the LDPC codes for low density parity check, if you're interested. And what they showed is that this is 10 times more efficient. So 10 times meaning that you need 10 times less physical qubits to encode a logical qubit. And this is what IBM will build the fault-tolerant devices on these LDCP codes. So how is it going to look? They call it the gross code. So gross actually means a dozen. And the way it will work, there will be 12 toruses of these things, 12 of these, and each of them will contain 12 logical qubits. So 144 logical qubits per gross code. And the way it works is that you will have 12 things. Within a torus, there is 12 all-to-all connected logical qubits. And in between the modules, they are connected by an L coupler, which is a microwave cable. And that's as far as I can go technically. But basically, it allows to perform 2-qubit gates between the different toruses. And then in fault tolerance computing, you have Pauli-based operations, which are Pauli measurements, which is how you implement your operations. And then to make it universal, you need the magic, which is a T-gate. So how do you apply a T-gate, which you cannot do just with Pauli measurements? For that, we have what is called a magic state factory. So this is just a part of the chip, so physical qubits that create a magic state. A magic state is something that you can use to implement a T-gate. It's basically 0 plus something with a phase 1. And you can use that state to implement a T-gate. Now, to do this, you do this in physical qubits, you do this with noisy operations. So the way it works, it's basically you need to create many magic states in a noisy way, and you need to create many because you want redundancy to make sure that you created one that is pretty accurate that then you can use to implement as a T-gate. So I think this can give an idea of how complicated this fault tolerance regime is going to be, because here you are only implementing your Cliffords. Every time you need a T-gate, you have to create something there and send it along the way to wherever you need it. Yeah. So one thing that we've been learning and we've been realizing that up till now, people, when they were optimizing circuits, they were trying to minimize the number of CNOTs because these are noisy and yeah, we need to reduce the number of CNOTs, or they were reducing the circuit depth because coherence, right? Now what we are realizing is that the CNOTs are actually pretty cheap. The problem is the number of T-gates, and depth, as we know it from a quantum circuit, is kind of meaningless because when we map things to this kind of gates, they will look completely different. So we are basically, one of my projects now is try to do some kind of resource estimation software to understand how do we even go about optimizing circuits in this regime. So, okay, they came up with a new code that uses 10 times less qubits. But now the next question is, in memory, you need 10 times less qubits, but once you try to implement gates, does this reduction still hold on? So there was a second paper where they show that if you take into account all the resources that you need, so if you remember the magic factory was in one end and you need to send things all along. So if you take all these things into account, it's still 10 times more efficient than the surface code. That's what they showed in the second paper. And then there is a third paper. I told you earlier that the decoding part is a non-trivial step. That's actually can be pretty expensive classically. So going from the syndrome to some operation that we apply classically. And it was not clear actually up to now, up till this paper, that with the type of new codes that they are using, you could do this step efficiently enough or in real time, because all these things that we are doing, the correcting the errors, they need to happen in real time. So in this third paper is where they show that, yes, indeed, there's a new algorithm that we can use for the decoding in real time. Yeah, this is kind of the roadmap of what they want to show from the hardware perspective. So this year, what they want to show is just creating 2 logical qubits. That's it, with some coupling in between, because within a torus, you have all-to-all connectivity. And all-to-all you cannot achieve in 2D. You need to have some 3D connectivity. Then in 2026, what they want to show is that I didn't touch too much on these guys, but this is basically what allows you to do also computation. So it's not just the 12 logical qubits all to all, but if you want to apply operations, you need to do something else. So here, what they want to show is that you can do this something else. Then in 2027 is when they will show this L coupler that connects 2 different toruses, so that you can apply 2 qubit gates in between the 12 qubits that are in all-to-all connectivity. And then in 2028, the goal will be to show one full implementation that has the 12 toruses plus the magic state factory, and that it works. And after that, in 2029, it should be the complete Starling chip. So, okay, we have, suppose that you have a fault-tolerant device, what can you do with that? This is, again, a pretty hand-waving graph, but here it's where what they did is basically try to look into different applications which are color-coded, and they are represented by blobs. And then within this blob, they try to find some quantum algorithms that exist and that we can compute what will be the runtime, and try to place them into what's the circuit size of when it's a useful problem and what's the circuit width. So this part here is the part we don't care too much from the quantum perspective, because this is what you can simulate with a classical computer. And this part is the interesting one. So the location icons, it's where the different devices will be. And the idea is that if we improve the hardware, these things would move further along this way. And here is where the algorithms, as they are now, fall in. And the idea is that with algorithm research, this should come closer to where the hardware points are. If you are just interested in browsing different algorithms that exist, you might be aware of this website, the Algorithm Zoo, where they list a lot of algorithms and then the speed up that you can get. So super polynomial is usually the one you care about, because polynomial, for example, Grover algorithm, which has a quadratic speed up, if you take into account all the overhead that comes from fault tolerance, it's not so clear that we will ever reach a scaling which is useful, because for sure at some point it will cross, but maybe it will cross for problem sizes that are just not practical. Now, I just want to go a bit briefly through some use cases, or more what's the hot topics that we are looking at the moment, also mostly in our group. So first of all, we divide the areas of research into 4, and here they are ordered by how near term or how far away they are. So many people, including me, we believe that the first application of quantum advantage will be some kind of dynamic simulations in chemistry, for example. That's why it's the first one. Then you have optimization and search, machine learning, AI, and finally numerical simulation. So numerical simulation, for example, solving systems of linear equations, PDEs, and so on. For these things, we know of algorithms that are probably better than classical. The problem is, for example, we don't know of practical use cases in which we know how to encode the problem into the quantum computer and get out the data without destroying the quantum advantage. So that's why it's the last. Now, for all of these applications, there's actually clients working with IBM on different topics, and they have projects. I will not go into those today, mainly because I just wanted to go through chemistry and optimization, because there is where we have a new algorithm and then a new benchmarking tool. So in chemistry, This is a graph over the years, the number of qubits that they were running, the different experiments on real hardware. And you can see that up to last year or this year even, it didn't grow too much. And the approach, so to simulate the dynamics, there are two methods. One is a variational quantum eigensolver, which is basically heuristic. And the other one is Trotter, which is analytic, but that you cannot do on near-term devices. So all these blue points, they are on the heuristic type of algorithms. The problem with the heuristic algorithm is that you cannot really prove that it scales for arbitrary system sizes or for arbitrary problems. And last year, there was a new algorithm called the sampling quantum diagonalization, or SQD. And with this one, they are starting to run much larger problems. So I don't want to explain too much what it is, but since it's a new thing, I just want to get a gist of what's going on. The idea is that you use the quantum computer just as a sampler. So for these problems, what you have to do is you have to diagonalize a Hamiltonian, a matrix that is very large. And here the idea is that you classically prepare some circuit that you optimize, and this circuit should have an overlap with the state that you are trying to find, some overlap. Then you use the quantum computer to sample, and you will sample bit strings. And then again, you use your classical computer to build a matrix that is much smaller than the original one. But if you diagonalize this matrix, then you obtain the solution. And then you can iterate and over. So the cool thing is that now the classical computer cannot just be my laptop. It needs to be usually for big problem sizes already HPC type of computers, so high performance. And the quantum computer needs to communicate with that. So there is a lot of work in communicating quantum and high performance computer. And I think it started kind of because of this new algorithm. So in terms of what can you do with that, there is this molecule that is considered to be a fault tolerance molecule. It necessitates of 72 qubits, and people try to simulate it. And it was calculated that if you were to do it with QPE, quantum phase estimation, which is an algorithm that is widely known to solve to find the ground state, but in a fault tolerance way, then you would need 4 million days and 13 days of runtime. So this was estimated with Microsoft Azure software, and it was for the surface code. Now, we don't have that. Say we want to run it on a noisy computer, and we use the variational estimation, so the heuristic algorithm. We would need 3 million years for that. The reason is because we need to do a lot of measurements. And now with the new algorithm, we would need 2 hours instead. And this is because it combines where classical is good at and where quantum is good at. And again, I won't go into these projects, but just to give you a flash, or in the past year, people using this algorithm have been simulating systems of these sizes, which are extremely large.
Is you make more efficient matrix computation, no? But the area of simulation is basically you have to solve big application problems.
No, so this one, it's actually a weird paradigm. What you do is with a classical computer, you prepare circuits from which you will sample some bit strings. Now, if you have some guarantees on the problem, and if you are smart enough in how you prepare the circuit, you know that these bit strings are enough to build a matrix that it's much smaller than the original one, and this you diagonalize with the classical computer. So I don't know if you've heard of Krylov methods. This is something that is used in classical computing. So what we are doing, if you know about it, is prepare the Krylov states with a quantum computer, and we sample from those. I cannot explain it better because I only know like roughly on the topic. I'm not an expert on, yeah. Yeah.
It's not, it seems to be now a recurring theme, but I first, fantastic work. It's great. But it seems to be a recurring theme that we combine quantum and classical methods, and that both, and decide that if you say that for this numerical evaluation, you basically exploit the Krylov method, but you actually use quantum computing for specific parts. Do you think that this will be, so to speak, the future of quantum computing, that you say, well, okay, we combine this stuff and we interweave it, and for particular operations we use quantum processor, or do you think that this is something that eventually will vanish and everything will be quantum?
No, we think it's going to be exactly a mixture of HPC and quantum, mainly because quantum can simulate a classical computer, but it's really bad for some things. Like it's a lot more efficient to do certain things on a classical computer.
Because then probably for specific methods you could build very specific modules that are then part of a hybrid computer. You would have a computer that, for example, does whatever specific numerical methods. Well, you would have like a GPU, so to speak, a specific subunit that does whatever you have to do here. That's great. That's really great vision.
Yes, I think in this case, it's more natural how you feed the data into the quantum computer, because you just need to prepare the Krylov state. In cases where, like, say, you want to solve a linear system or something like that, for which we know that a quantum computer is pretty good, loading the data is not so trivial anymore.
Yeah.
Now, for optimization here, I'm not going to present applications themselves, but just want to present a new project that's going on. So in optimization, what we look at is, first of all, if you have an NP-hard problem, it doesn't mean that all instances of this NP-hard problem are hard to do. Some of them might be easy, so you don't want to focus on those. Then for a lot of algorithms, there is no performance guarantees. Even classical algorithms for optimization, they are heuristics. So how do you compare things? That's a bit tough. Yeah, many problems can be solved efficiently. And then up to now, we didn't have benchmarks in which you can run both classical and quantum algorithms to compare, okay, which one is better. It was people running quantum algorithms on some problems, classical people running classical algorithms on other problems, and how do you claim one is better than the other? It's not easy. And also, like, from the quantum community, if you are not an expert in optimization, how do you find problems that we know they are hard to apply your quantum algorithm? So with this idea, now we have a quantum optimization benchmarking library. This is completely open source. And the idea is that this came out from one of the working groups that I mentioned earlier. So they identified 10 classes of hard problems in optimization. And what this GitHub contains, it's these 10 problems. For each of them, they have different instances of increasing size and increased hardness. And then also some guidelines into submissions that you can do on what metrics are important. So the idea is that if you have a classical or quantum algorithm that you think it will be good in one of these problems, you run it and then you upload your results. And in that way, we can compare apples to apples. So if you are interested, please have a look. Also, if you are interested in what are the problems that have potential for quantum advantage, they are in this white paper, and the link for the optimization benchmarking library is in there, in case you're interested. And now, to finalize, since this was AI weeks and I didn't say anything about AI, how are we using AI for quantum at the moment for transpiling circuits in Qiskit? So if you want to run a circuit, you need to map it to some connectivity map. And there is classical algorithms to do so, but this is actually an NP-hard problem, how to do it optimally. So now we are using AI to try to enhance the transpilation and try to optimize gates that could be canceled out potentially. And there is also some code assistance. And with that, I'm done for today and would be happy to take any questions.
Hey, yes, please, Thomas.
I'm always impressed with the roadmap of IBM. It looks like certainty, but it's kind of forecast. Do you have data how accurate this roadmap was in the past?
I would say not very inaccurate. Like it never struck me as they promised this and it never came out. I'm sometimes also surprised because obviously I'm not there designing the roadmap. I have not much say in the hardware. Sometimes surprised what they come up with, but usually maybe it gets delayed by 1 year. Maybe I saw that once, but it's quite on.
Do you have an explanation for that? Because in other fields of research, you're off by 15 years or so.
I guess they don't promise things they don't think they can have. I don't know. I guess there is a lot of ongoing research and you can get an idea of maybe this will work by then or not. So in many cases, some of the devices that get deployed, people have been testing them beforehand. So when something gets deployed, it's not that it hasn't been tried. Maybe we've been using it or somebody has been using it. But also, I don't know everything because some stuff it's only for US people.
Questions? Yes. Yes.
What do you think makes the quantum machine learning harder than quantum optimization? Because I also read this paper, but I also noticed that at least in Zurich, there's not so much coming out in quantum AI anymore. Is it too hard, or is it just you need too many gates that you can do something useful? And
so there were some people doing quantum machine learning, but the community from that side, they've realized that it's not very clear how or if quantum can be applied. They are trying to find exactly what would be the best approach, because for optimization in the end, there was always Grover search. So in the worst case, you can say, I apply Grover search, and here there is something now. Of course, there is a bit more convoluted algorithms. There was also quantum annealing, which is a bit more analytical in the sense that if you have a quantum annealer, you can find your answer. And then from there, they created new algorithms. For quantum machine learning, I think they've been trying on problems just to run some heuristics and trying to see if something comes out, but there is like not a lot of structure. And yeah, I think the consensus was that they don't know yet. And then within IBM, now we are more focusing on optimization in our group, chemistry, physics, and then a bit more foundational research. But yeah.
Do you at least have some theoretical work where you can show that it should be some advantage?
I think there is some theoretical works from maybe the James Insert group, but I'm not too familiar with the field. I've been working mostly on, in the past, Hamiltonian simulation, numerics, error mitigation, now more in the fault tolerance regime. So I never really touched too much on the heuristic parts. But yes, there should be some theoretical works. There is also, I think, on...
Basically, you learn in noise model, and then basically you transpile it based on what kind of circuit combination shows the lowest.
So there are two approaches for error mitigation. The one they used is what's called probabilistic error amplification. So what you do is, as you say, you learn the noise model. For that, you need to assume that the noise model looks certain way. And then you need to assume it's sparse enough, because if it's not sparse, meaning that if you apply a gate here, something else happens here. That's what, if that happens, it's not sparse. So you assume it's sparse because it's unlikely that things will affect things far away. Then you can learn the noise efficiently. And then what you do is you have a mathematically error model. It's a series, an exponential series. And what you can do is you can write the inverse map, which is a non-unitary gate, and then you can apply what is called probabilistic error cancellation. Because what you do is, by sampling gates from this map, you can implement the inverse map, which you do by combining many circuits and then combining the results classically, and then you cancel out the noise. This comes at a very hefty price, so it becomes exponential in the noise. Or you can do what they used in the utility paper, which is error amplification. what you do is you say, okay, canceling out the noise, it's pretty expensive. What I can do is make things worse. So I can increase the noise, and then you run it for like different noise levels, and then you can plot the results on a graph. And if you have assumed that the noise looks certain way, then you can also claim that the noise should increase with a certain curve, and then you can fit this curve and then take the value that corresponds to zero noise. And that's the mitigated value. But there are a lot of assumptions in place.
Any more questions? No? So clear. Okay, nice. Then thanks once again. I'm going to stop the recording so that later on we can send it.